All right, so here's a video on end behavior, just a few more notes to add to the video, or maybe some more examples that will help you out with homework or Pearson, or just knowing this moving forward in topic 10. So first, the basics of end behavior is that it is trying to determine what is happening at the ends of the function. Now, the ends of the functions most likely are not points, or they're not like solidified places. They are arrows, which means the function is continuing on past what we can see. So that's why it's a good idea for us to know what's going to happen to that function as it moves past this point that we can see on the graph. So the way that we express end behavior is in terms of like infinities and negative infinities and sometimes actual values. You're going to see end behavior dealing with x's and y's, all right? The reason we have x's and y's, or x's and f of x's, because those are the same thing, is because the x-axis stretches right and left. The y-axis stretches up and down. So by using these variables, we can describe what's happening to the function as we go to the right, the left, as we go up and down. Okay, so when I say x is going to negative infinity, this first point right here, that's negative infinity is going to the left, because all negative numbers are over here. Like I should have had left and right, because that would make more sense. If I say x is approaching infinity, or sometimes you'll see positive infinity, positive numbers are going to the right. So this is just a fancy math way of saying left and right. When I use f of x, which is the same thing as y, when I say f of x or y is going to negative infinity, that really means it's going down. When I say f of x is going to positive infinity, that means it is going up. I have a few examples here for us to look at, and when I teach this in class, what I usually use is a little stick person. So here's my stick person. We'll call it Miss Krupp right here. And I imagine this stick person walking along my red line, or my function, and seeing where this person is going. So this first line, we'll go through slower on this one, as x is going to negative infinity. So again, what that means is as I'm going to the left, okay, so I'm going to move my person to the left here. Now it's going to move everything, unfortunately. This person, as I move to the left, is going down that line. So instead of using the word down, we use some math lingo. Down would be negative infinity. Okay, now as I move my person to the right, which is x going to positive infinity, let's see where Miss Krupp goes if I move my person to the right. Now I have to follow that red line, so that person, or Miss Krupp, is actually going up. Well, another way of saying up, in math, is to say it's going to infinity, or positive infinity. All right, we got another person here. We're going to talk about what is going to happen to Miss Krupp as she goes to the left or the right. I'm going to start in the middle, all right? It doesn't really matter where you start, because the end behavior is always talking about, okay, as I go to the left, where is Miss Krupp going? Well, if she's walking along that function, she is going down, and so we say negative infinity. As Miss Krupp is going to the right and following that function, she is also going down, so she is going to, negative infinity. So again, when x is negative, it's saying to the left, and when f of x is negative, it's, saying down, not up. That would be bad, okay? This is saying as x goes to the right, the function is also going down, or the arrows are pointing in the downward direction. I think the exponential functions are probably the most difficult, because they are the ones that aren't necessarily, or they're not, both ends are not pointing up or down. One of the ends up flattening out against what's called an asymptote. So Miss Krupp is going to get on this line, and as she goes to the left on this function, she's actually going up, okay? So I would say up is positive infinity. Now, as Miss Krupp goes to the right with this function, gosh, she's not actually going down. She's getting really flat and kind of flattening out against an asymptote. I picked one that was a little bit different than in the notes example, just to kind of give you an idea of what you need to pay attention to. But a function being shifted up or down is controlled by that last. is controlled by that last number, or that +2. So this function actually has an asymptote at 2. So Miss Krupp is never going to go down here because it doesn't go down there. It's flattening out against the asymptote, which in this case is at 2. So as Miss Krupp goes to the right, she's getting closer and closer and closer to 2. This is the one kind of special case with exponentials. All the other functions usually are to positive infinities or negative infinity. Remember that plus, oopsies. Quadratics, much like absolute value functions. So we're going to start going to negative infinity or to the left, and Miss Krupp is going up. And as I go to the right, or positive infinity for x, I am also going up. So in both of these cases, our end behavior is going to positive infinity. So again, really quickly, as a reminder, as x goes to positive infinity, that means as my Miss Krupp, as my person goes to the right, my function is going up. Same thing, negative infinity is to the left, and the function is going up. Last example here really quickly, cube root functions. So if I start kind of in the middle as I go to the left, now cube roots are always kind of a mind mess for me because a lot of times they look really, really flat. And so they look like an exponential curve. But what's happening here is that these curves are increasing very, very slowly in some cases, but they don't actually have a stopping point. So as Miss Krupp keeps going and going and going and going and going and going, she is slowly going up the entire time. As I go to the right, the same thing happens. A lot of times cube roots or square roots look like they flatten out like an asymptote, but in fact they don't. She is going to constantly be getting lower and lower and lower and lower. So one more time, as I go to the left, or as x goes to negative infinity, Miss Krupp is going up. So she's going to positive infinity. And as I go to the right, Miss Krupp is going to keep going down, so she goes to negative infinity. We want you to have a good idea of what these graphs look like, but if you're ever at a homework question or something where you're stuck and you're saying, hey, I don't even know what this equation would look like, use your graphing calculator and graph it, or plug it into Desmos, or use that link that we have on Schoology for you to access a graphing calculator. I hope that helps. Have a great day.